So,
Does everyone see this?
yes, we can see your screen. So
All
I
right.
think you can start. So you're going to Neil Cornish about a global approach on laser analysis and gravitational wave background, cosmological background, sorry. Go ahead, please.
All right, thank you. So I was going to say a little bit today about how searches for stochastic backgrounds with LISA fit into the overall analysis. We often, when we're working on different parts of the analysis, we might be thinking about different source classes like massive black holes or galactic binaries and stochastic signals and Henris. But in practice, all of those signals are in the data simultaneously, so you really have to do an analysis that takes care of all the signals. This slide here is taken from the second LISA data challenge dataset, so-called Sangria dataset, where we've got a full galaxy simulation of tens of millions of galactic binaries, in addition to a collection of supermassive black hole binaries, which are sort of isolated here. And this one doesn't have a stochastic background, but there are other data sets with stochastic backgrounds in them as well. And in practice, we're going to be dealing with this kind of situation. So how do we work in our analysis of a cosmological background with LISA with all these other signals? So just as a reminder, for those of you that aren't so familiar, LISA is really three interferometers in one. We have the triangular configuration, and you can extract Michelson-type signals from each of the vertices. But from those, we can form up these combinations, which are so-called A&E combinations, which instantaneously measure the plus and the cross polarizations of a gravitational wave, and then another combination which in the case of general relativity, at least at low frequencies, would corresponds to like a scalar breathing mode, which general relativity does not have. So it's a null channel, which is useful for monitoring noise properties. That's all at low frequencies. At high frequencies, all three channels start to respond to gravitational waves. So here's just a little simulation. This is just a simulation of 4 hours of LISA data. It's a very simplified simulation where only a small number of signals have been included. So this is in the time domain. If we transform that to the Fourier domain, there's a few little spikes showing up. And if we clean out the noise, here it's got a collection of sources. We have some of those individual spikes are galactic binaries. We have I think one Henri here and one black hole. And if I separate out the components just from what was injected, you can see that in this case there was 25 galactic binaries, one Henri, and one supermassive black hole. And this, of course, is a vast simplification over what the real situation will be. There'll be tens of thousands of galactic binaries that we can resolve. There'll be hopefully tens or hundreds of extreme mass ratio inspirals, and again, tens or hundreds of supermassive black hole binaries, in addition to stellar origin black holes, like we've been detecting with LIGO and Virgo, and other types of sources. And then in addition, hopefully, some kind of stochastic signal, perhaps from the early universe. So we have to, with one data set, be able to pull out all of these signals. So if you write down some kind of likelihood function for the analysis, under the assumption that overall we're going to have something like Gaussian noise, which might be naive, but this the data then is containing all these signals. So your model is a sum over n gravitational wave signals, which you don't know in advance how many there are. You've got your noise correlation matrix, and you've got this huge number of parameters that you have to deal with. So the model parameters here are going to include parameters associated with the signals and parameters associated with the noise. So we've got the various types of signals that we might be searching for, including both astrophysical backgrounds and also primordial backgrounds. So in addition to the resolved sources, we will also have components that are unresolved. And that might be unresolved galactic binaries, unresolved extreme mass ratio inspirals. There might be unmodeled burst signals in there. And one type of source that we're particularly interested in, and you were hearing about today in the contributed session, the cosmological sources and possible primordial stochastic backgrounds that would be very interesting, telling us about some early universe physics. Well, while modeling all of the signal components, we also have to model the noise contributions. And so we've got acceleration and position noise contributions on each spacecraft. There might be various kinds of glitches like we see in the LIGO and the Virgo data. There'll definitely be some gaps in the data. So we have to do some kind of infilling of the gaps. We also have to model the orbital dynamics because that actually goes into setting up this virtual interferometry that we do with the time delay interferometry. So we need model parameters for all of those, and sort of a rough estimate for a 4-year data set, the dimension of our model could be approaching 1 million parameters. So this is a quite challenging analysis, very different from the sort of 10 or so parameters that we deal with currently in LIGO for a typical binary black hole system. What is additionally challenging is we don't a priori know how many sources are going to be resolvable. So you can't just set up a model where you're looking for 5 black holes and 10 Henris. You actually have to explore the possibilities that of how many sources you have of each type. So you have to do some kind of a trans-dimensional model selection here where you explore the dimensionality of your model as well as the parameters. Now, this global solution, what was appearing in the numerator of that likelihood was the chi-squared here, where C is the noise correlation matrix. And if you expand that out, the first term is the individual chi-squared for each source. And then you also get a term that involves the overlap between sources. So if that inner product between sources I and J didn't exist, you could just go ahead and just work one source at a time, and that would be fine. You get the answer would come out. But the problem is there are these overlaps. When you actually look at the size of the overlap between, say, a galactic binary and a black hole, it's actually quite small. But the problem is there are millions of overlaps, or at least thousands of overlaps amongst the resolvable sources. So the individual overlaps are fairly small, but there's a lot of them. So when they combine, they're actually quite a significant problem. So we have to do this analysis in a global way that incorporates all the correlations. And that really sounds daunting. So we've been thinking about ways to do this that doesn't horribly correlate all of the different analyses that are being done in terms of having to know exactly everything about Henris if you're also wanting to do stochastic backgrounds. So one way to do that is in a framework where you what's known as blocked Gibbs sampling. If you're doing a Bayesian inference using Markov chain Monte Carlo techniques, where basically what you do is you update one component of the model, then you update the next component of the model, and so on. And it turns out that even though you update each block, for example, the ultra-compact binaries, the galactic binaries, then the supermassive black hole binaries, the stellar origin black hole binaries, the unmodeled gravitational waves, the Henris, the stochastic, if you just cycle around and update each term in the model sequentially or in any order actually, you will still capture the correlations, even though you do each update independently, because as you move on to the next block, that builds in the correlations. So while we do need to do a global analysis, so long as we just sort of update each component and then sort of pass the residuals, so data minus model, from one block to the other, then we end up getting the fully correlated solution. So people can work on Henris without having to worry too much about what other people are doing, because ultimately they'll just be working with the residuals from the previous steps and passing this around. So the kind of scheme that we're setting up, at least a group of us are working on now, is this trans-dimensional Bayesian inference. So this is where the model dimension is not yet determined. All of the analyses, we're in the process of moving all of our codes into the wavelet domain. I'll explain why in a moment. We're using this block Gibbs scheme where we update each component of the model. And another key thing is that it's a time evolving solution. So, starting from when the LISA detector first turns on, we'll have data from the first week. We'll analyze that. Then we, as new data comes in, we keep on adding that and updating the model. So we're doing a time evolving solution as we add data in from week to week, and so that's the overall scheme that we're working on. Now, just a word about this transdimensional modeling. Here's an example where a degree D polynomial is being used to fit a collection of data points, and the blue traces here are samples from a transdimensional Markov chain Monte Carlo that was fitting these data points, and the little inset is a histogram of the model dimension, and you see that the preferred model dimension was a 7-dimensional polynomial, but it also tried polynomials with 8, 9, and even 10 parameters, but it favored using a 7-parameter polynomial, 7-term polynomial to fit this. And so here's an example where both the components of the polynomial, the various terms in the polynomial expansion, are getting varied, but in addition, the degree of the polynomial is also varying. So this is a very simple example of this, what we mean by transdimensional modeling. Here's a more pertinent example from the LISA data analysis. So this is an analysis conducted in collaboration with Tyson Littenberg and Kristen Lakis and Travis Robson, where we have the simulated, this was from the so-called Radler data set in the LISA data challenge. So this data set just had instrument noise, simulated instrument noise, and galactic binaries. And you can see the the colored components here are the resolved galactic binaries that were subtracted out. And we didn't know in advance how many binaries would be resolvable. So this is using this transdimensional modeling. And if you're interested in this, we've got a paper, but we also, if you actually want to download the code, it's available on GitHub, free to anyone to play with and can assist in the development. In the most recent data set, we have the so-called Sangria data set. We have a collection of massive black hole binaries, and the upper plot here is a blink map showing the time frequency map of 1 month of data. It's actually month 2 from the Sangria data set. There was a very loud, I think, signal to noise 1500 or something, massive black hole binary there, and it was so loud in the lower plot. The two simulations, unfortunately, are not quite timed here, but you can see that the power spectral density that you infer is actually highly distorted by the presence of the black hole. So you have to do joint inference of the supermassive black holes and the power spectra, because the black holes actually are so loud that they throw off the power spectral estimation. So you do it jointly rather than, and you can't use off-source data to estimate the power spectral densities in LISA because there is no off-source data. Everything always includes the sources. So this has to be done simultaneously, which is something that we do in the context of LIGO data analysis with the Bayes wave algorithm. So it's the same idea here applied to LISA. And then we expect that the noise in the LISA detector is going to be non-stationary. We're talking about detectors running for years on end, and even if by some miracle the detector noise is stationary, the astrophysical foregrounds, the unresolved components like the galactic binaries, will definitely produce a non-stationary effective noise. So what to do about that? If the noise is non-stationary, the noise correlation matrix is no longer diagonal in the Fourier domain, so that can then lead to quite costly matrix inversions. So a way around that is to switch to using discrete wavelets for locally stationary noise, that is noise where the noise properties are varying sort of slowly with time. The wavelet transformation is then diagonal in the wavelet domain, so it means that it's very easy to calculate these inverses, which often involve millions of points. So inverting a million by a million matrix is very expensive, so unless it's diagonal. So there's an advantage here by working in the wavelet domain. It's nice and diagonal. And then we model the spectrum. The spectrum is no longer just a function of frequency. It's the time frequency map of whitened LISA data. It was whitened assuming that the noise was stationary, and you can see that that didn't do a very good job because there's components here from the galaxy that actually get brighter and dimmer over the year. And so we actually then model the spectrum as a function of time and frequency. So we have a dynamic or evolutionary spectra that we model. And here's an example for a simpler example. This is an autoregressive time series with a time-varying correlation parameter. So you can see that there are times when the noise gets larger and then smaller, and you can see this in a time frequency map. This is actually a fit to the dynamic spectrum. So you see it both varies in frequency and in time. So we're directly modeling the time and frequency dependent of the noise properties. And to do that, you also need since we're moving the entire analysis to the wavelet domain, we need waveforms in the wavelet domain. So been able to figure out ways to directly calculate the waveforms in the wavelet domain. And it turns out there's an added bonus because a time frequency track of, say, a galactic binary or a massive black hole binary, it's a line in time frequency space. So the length of that line scales as the square root of the number of data points, whereas a time domain or a frequency domain analysis, the size of the signal scales linearly with the number of data points. So it actually turns out that the waveform generation and the likelihood evaluation in the wavelet domain is way faster than in the frequency domain or the time domain. So not only do you gain the advantage of being able to properly model non-stationary noise, the actual analysis is way faster. So it does a better job, and it's also faster. That's rare that happens. Usually you pay a price for being more accurate. Here, you more accurately model the noise, but the analysis also speeds up. So we're in the process of modifying all of our codes so that we've done that now for the galactic binaries, the stellar origin black holes, and in the process of doing it for the supermassive black holes. So all of the analyses now are going to be wavelet domain and much faster. Okay, so back to the main topic for the day. How do cosmological stochastic signals fit into this global solution? Well, with a stochastic signal, we're not so much interested in what the individual, I'll switch back to the frequency domain here for the moment, just because it's more familiar, I guess. We're not really interested in what the individual real and imaginary parts of a signal, of stochastic signal, equal, because that's random, right? It's stochastic. What we're actually interested in is the power spectrum, for example. So what you can do is you can introduce a prior that says that for example, that the individual components are distributed, Gaussian distributed with this power spectrum. And then you just integrate out over the individual samples for that stochastic signal. And when you do that, what happens is that the stochastic signal moves from the numerator into the denominator. So here, the big I and J, this is the noise weighted inner product now for that includes stochastic signals, the big I and J refer to which detector, and we have this correlation matrix now, which is known as the overlap reduction function, which tells us about the correlations between the different detectors. So instead of just having the noise, which hopefully is uncorrelated between detectors, so a Kronecker delta here, we then have terms that are correlated between detectors, which encode the stochastic signal, right? So that's the standard analysis that we think of in terms of like cross-correlation, but it's not really cross-correlation. It's just integrating out the stochastic signal. So we move it from the numerator, where data minus model, and it ends up in the denominator. In the case of LIGO, this is the overlap reduction function for the LIGO, Hanford, and Livingston detectors. Unfortunately for LISA, it doesn't quite work like this, because these data channels, these A and T data channels, they actually have vanishing overlap, at least at low frequencies. So we don't, you're not actually doing the stochastic analysis with LISA by doing cross correlation. So instead, what you're relying on is hoping, at least, that the signals and the noise have different spectra. So if the signal in this little plot here, the signal here in green, the noise in red, and then we've got the galactic component, which varies during the year, in blue, because they have different spectra, we can hope to separate them using their different spectral properties. So that is familiar in, say, cosmic microwave background analysis, where on the left here you see the different contributions to the microwave background as a function of frequency, and then on the right you see the different maps that you can make at each frequency, and at different frequencies, for example, at 60 gigahertz and 100 gigahertz, you're more dominated by the CMB component, whereas at lower frequencies you don't, you start picking up, say, synchrotron. At higher frequencies, you get some of the thermal dust contributions. So by measuring the CMB at different frequencies, you can actually separate out what component comes from is primordial, and what part, say, comes from dust in the galaxy. So it's very much the same idea here, that we're going to use spectral component separation to do the analysis. Now, in 2016, I was invited to a LISA Cosmology Working Group workshop in Hamburg, and some of the organizers, Chiara, who's on the line today, and Germano, kept on asking, how well can you subtract a stochastic signal? And this was very puzzling to a lot of the data analysis people in the audience, because people didn't really think about gravitational waves analysis for stochastic signals as being subtraction, but it is actually subtraction if you leave the signal up in the numerator. So here's an example. I actually put this together during that meeting. I wrote a code to do this in my hotel room, and back when we used to travel to meetings. And so I put in just a power law model for the noise, and then I did a sort of a mixed power law model for the signal, these various components, and then here's a sort of a simulation showing the data and the signal in two detectors, and then analyzing that either in the one detector case or the two detector case. You see that we actually recover nicely all the different the amplitudes and slopes and the knee frequency for this signal model, and we also recover the noise parameters. With two detectors we do better, but we still do okay with just the one detector, which is more relevant for LISA because we don't really have correlations. This was 100%. This had a overlap reduction function of 1, so these were perfectly aligned detectors. But notice down here, so that's all the standard stuff. That's how you extract those components. But here, this is the match. This is the actual standard sort of match calculation that we do between templates and injected signals. And you see that the match is around 0.45 for the case of one detector, and around 0.58 for two detectors. So this is actually because I was modeling not just the hyperparameters of these models, I was actually modeling the individual real and imaginary parts at each frequency, right? And then taking those and calculating the inner product with the original injected signal, we actually are subtracting out about half of it with the one detector case, and we do a bit better, about 60% subtraction in the two detector case. Now, as you increase the number of detectors, that subtraction gets better and better, and it will approach unity with, you know, a large number of detectors. So you literally can solve for the individual stochastic components and subtract them if you want. And indeed, this is the way that stochastic analyses are done in pulsar timing. In pulsar timing now, the stochastic waveforms are kept in the numerator. They don't appear in the denominator. And here's an example that was originally from a paper by Lentardi et al. This plot is actually from the Nanograv 12.5-year paper, and those gray bands are actually the recovered signal strengths as a function of frequency, modeling, trying to directly model the real and imaginary parts, or the sine and cosine components on a Fourier basis of the actual stochastic signal. And the reason that it's done that way in pulsar timing is that the matrix inversion is extremely expensive because it's not diagonal, it's not stationary, and it's all done in the time domain. So by keeping the signal on the numerator, it actually simplifies the matrix inversion. So it's much faster to actually just directly simulate and solve for the individual components of the stochastic signal. So in the case of LISA, we use this spectral separation. You've also got the galaxy, which sort of has a level that varies with time, right? So here's the overall, here's the full galaxy. This is over a year. You see it's varying. You subtract out the bright signals, you get left behind with this green component. And then you've got the LISA noise, and then you also have a simulated gravitational wave signal in here, gravitational wave stochastic signal. And the key point here in this case is that, this is from a paper I wrote with Matt Adams back in 2013, is that from the resolved component of the galaxy, it tells us exactly what the spectrum and time variation is of the unresolved component. And that's going to be true for all of the astrophysical foregrounds, that the resolved component is going to tell us very accurately what the spectra of the unresolved component is, so we can subtract it out. And here's a plot showing this. You see the galaxy level varies with time over the year. Here's the simulated signal, and we're able to extract that signal with this spectral separation. And also we had a very good model for how this galactic component was varying in time, because we'd actually resolved the rest of the galaxy. And so we're able to then recover the gravitational wave amplitude and its slope, and also the noise parameters, all in a joint analysis. So this is the kind of thing that we're going to do in the full LISA analysis. So to conclude, stochastic signals fit naturally into the LISA global solution. You can either keep them on the numerator in the usual data minus model, or you can integrate them out and put them in the denominator. I don't necessarily see any great advantage in keeping them in the numerator here, but if you did some kind of nonlinear operation on the data, maybe associated with gap filling, that would actually break this equivalence between having the signal on the numerator or integrating it out to the denominator. So we might actually need to fit directly like we do in pulsar timing. So if needed, we can indeed subtract stochastic signals, as Chiara was wanting us to do. And a really key point that I'll leave you with here is that the stochastic components that aren't from the early universe are highly constrained in their spectra are highly constrained by the resolved components. So we can do a very good job of fitting those out. All right, thank you. I can take some questions if.
Thanks a lot. Yes, I see David's hands rise, so please go ahead.
Hi, Neil. A nice talk. Could you go back to 22 or thereabouts? I want to ask two questions. Yes, okay, good. One of my questions had to do with the plot on the bottom that I think you just talked us through. I misunderstood at first and thought that these were different instrumental noise spectral features, but in fact, no, they're astrophysical, they're external, and they're something that you can exactly treat as they do in the CMB search or something. Why do I have reserve two questions. Here's my first one. Channels have zero overlap at low frequencies. That must be some effect of the TDS or something, because if you had simply independent interferometers, say like in the ET model, you would be able to resolve out common signals between the two, right? Why is the overlap?
Yeah, so but A and E, A is like measuring, say, purely just plus, and E models purely cross. And for a stochastic signal, those are uncorrelated, so you get just zero because one's purely plus and one's purely cross, and T's
that's fine,
which doesn't respond in GR. So they're signal orthogonal. So the A and E channels, one's just for now. Of course, if it's a say it's a binary, quasi-circular binary, the plus and the cross are just out of phase with each other by pi, right? So when we actually are doing a phase coherent kind of analysis, that's fine. We can use the plus and the cross because we know what their relative phase is, so we can still coherently extract them. Here, because the phase is random, the plus and the cross have zero cross correlations. So these are signal orthogonal for stochastic signals.
There still is there is non-orthogonal information that comes from the three arms and could be analyzed for the correlation between the non-orthogonal component, no?
Certainly at high frequencies, these are no longer orthogonal, but at low frequencies, they're precisely orthogonal for stochastic signals.
In that basis. Okay, good. I'll think some more. Other question had to do with computation. I think you called it Gibbs blocking, this iterative process of allowing one to think about the evolution, well, to be able to cycle through analyses and progressively resolve out and improve your model. Right. The obvious advantages to this approach, it must be ineffective or inefficient, I should say, computationally. And I wonder if there's a measure of that, and if it matters, maybe it doesn't matter.
Yeah, that's a good question. So if there was large correlations between the blocks, it's inefficient because, I mean, unfortunately, I didn't include a really simple example of Gibbs sampling. Like if I have just a two-dimensional, parameter space that's got like a big correlation along one direction, Gibbs sampling means you jump in one direction, then you jump in the other, and that can be highly efficient exploring highly correlated parameters, right? You really want to be sort of jumping along the direction along the correlations. But in these cases, the correlations between these blocks are really small. So there are correlations. You do have to care about them, but they're very, very small. So updating the blocks where there are correlations, and then just cycling onto the next one, and there's not much correlation between blocks, is actually highly efficient. And you're just passing residuals around. So it means that we can kind of wall off the analysis. So for example, we're currently with Tyson, we're joining together the galactic binary code with the supermassive black hole code that we have, but we're not actually integrating the two codes. We're just making it so that one passes its residuals to the other. So the two codes are still, not all glued together. So it makes development much easier because it breaks the linkages between each of these blocks. I think it would be a nightmare if we actually had to join together every single analysis and make them all part of one code. So these codes can be all written in different languages, and people don't have to know anything about what the other one's doing. It just passes along its residual, just data minus its model, and passes along to the next block. So it really breaks the correlations between research groups, which I think is going to be necessary if we ever hope to do this.
Right, good. That's not so much, well, at any rate, that is certainly a very, very strong advantage. How does the instrument model impact the efficiency of this approach?
Well,
is it, well, go ahead.
yeah, so I mean, that's modeling the noise and also the TDI parts
Yeah.
of the orbit and everything. So that's having to be sort of, simultaneously updated as you go along. And, just to give you the perspective from, say, pulsar timing, the noise model and the number of parameters in the noise model is vastly larger than the number of parameters in the signal model, right? So most of the effort in pulsar timing goes into the noise modeling,
Yeah.
which is something that we're starting to see a bit more of in the LIGO analyses, where we're putting a lot more effort into the noise modeling as well. But certainly already for pulsar timing, it's the dominant cost is modeling the noise. And I think it'll be similar for LISA. There'll be a lot of parameters that we're going to have to fit for the noise modeling, the instrument modeling.
And that can be effectively approached using this Gibbs blocking approach.
Yes. Yeah.
Okay, well, thank you.
Thanks a lot. So we're a little bit behind schedule, so I think we are okay for the question. Sorry. And so we can switch to the next speaker, Ariana.